Hey guys, it is Mr. Schwanekamp. Good to see you. Even though I can't see you, I still feel like we're together. Hopefully everything's going all right with you and you're making it through this crazy time. We today are working on section 2.2, and we've been doing that for a while. Today we are doing 2.2e. So this is like the fifth part of this chapter. Basically, the whole chapter is in 2.2. It's weird. Okay. Today we're going to be focusing on something really important. We're doing particle motion. So we were talking about velocity, position, acceleration, how those three things connect to each other. It's really important. We are going to do this today. This is unit 2. We'll teach you it again next year in unit 5, and then we'll teach you again in unit 8. And so a big incorporating concept is this particle motion, and we're going to do it a lot. Let's get the basics done today. This is a 2-day lesson. We'll do some notes the first day, and then the second day you'll kind of apply those notes to a practice. Let's see how we do. So a lot of what we're doing today is vocabulary and you understanding that a little bit better. So first one here, it says displacement is a big thing. We're talking about particle motion. Displacement is going to be a phrase that's used all the time. Displacement is the change in distance from the initial time to the ending time. So normally I would get up in the front of the room and walk around like an idiot for you, but I can't do that here. So imagine you have this number line. This is 0, this is 1, this is 2, this is -1, this is -2, this is -3, and 3. Let's say you started right here at 2 and you walk forward 1 and you stopped. What is your displacement? Well, your displacement is 1 because the total change in your distance was 1. Okay, let's try it again. Let's start this time. Let's start here. I'm missing a line. Let's say I started here at -2 and I walked forward to 1. My displacement is 3. I'm going to walk back to 0 and then forward to 2. So I went forward, back, forward, and I stopped right there. What is my displacement? Well, my displacement is 1, 2, 3, 4. My displacement is 4 because I went from -2 to 2. Or in other words, you take your ending position minus your starting position. I get 4. Okay, that is displacement. Obviously, we could do lots of different things with displacement. For example, if I started at 0 and I walked forward this much, and then I ran backward to here, and then I ran forward to here, and then backwards, and then forward, and then backwards, and then forward. But then I stopped at 0. If I started at 0 and stopped at 0, my displacement is 0. Boom, done. That's all I need. Okay, so displacement is your change. Ending minus starting position is going to be the key. Okay, the position of a particle is measured. The position of a particle moving along the x-axis is given by this equation right here. Notice that they use the phrase S of t. S of t is often going to stand for position. Okay, that is kind of some abbreviation they'll use. They will often also use x of t, which gets annoying, but the AP exam throws it at you, so I just want you to see it. Okay, so this equation will tell me position. Okay, so for example, if I found S of 2, that means I'm plugging into this equation, and it will tell me what is the position of the particle when your time is 2, and so on. So we want to find the displacement between 0 and 2. So to do that, I want to find S of 2 and S of 0. Those are the two numbers I need. So I'm going to take 2, I'm going to plug it in. No, I don't want to do this math. It's late at night that I'm recording this. So 2 cubed is 8 minus 16 times 2 squared would be 4. So 16 times 4 plus 15 times 2. Oh my goodness. 32 minus 64 would be -32. Plus 30 would be -2. Now I'm sure I made a mistake there, but I'm just going to act like I didn't for the time being. S of 0, sorry, my calculator kept popping up. S of 0, I can do S of 0. S of 0 is 0. So if I want to figure out what my displacement was, I'm finding the displacement between 0 and 2. So we're going to take our ending position. So that would be the -2 because I stopped at 2. Because time, we go from 0 to 2. -2 minus 0, my displacement is -2. Or in other words, here's what happened. We started at time equals 0. What was my position at 0? It was at 0. And then I went back to -2. So my displacement was -2. That's it. Okay, we could do the same thing with 1 and 3. We hopefully understand displacement. This is an important next step, average. Okay, for example, often we would say something like average rate of change. That is so far where you hear the word average. And we'll do average a couple different ways in calculus, but today we are talking about an average rate of change. If we want to talk about the average velocity. So for example, you are driving on vacation and I want to know what is your average miles per hour during your trip. That's your velocity, your average velocity. What was your average velocity during your trip? What would you need to know? Well, to find your average velocity during the trip, your miles per hour, you would need to know how many miles did you travel and how many hours did you go. So for example, I traveled 600 miles and I did it in 10 hours. Well, then what was my average velocity? My average velocity was 60 miles per hour. That's a rate of change. All right. We took a position, we took miles, which is our position, and we put it over our time. Miles is our displacement. That's how many miles I was displaced from start to end. It was 600 miles. And my time was hours. I went from 0 to 10 hours. That's just slope. That is y sub 2 minus y sub 1. If I gave you some ordered pairs would be 0, 0. Because at time equals 0, I was gone 0 miles. And then at 10 hours, I've gone a total of 600 miles. That is slope. That's average rate of change, average velocity. It's just a slope. Okay, so don't get overly overwhelmed with that. Given the distance function, this thing right here. So S of t is going to tell me distance, position. I don't like that they use the word distance there. I need to fix my notes. That's a position function. Given the position function, S of t is equal to that, where S is in meters and t is in seconds. Find the displacement. All right, cool. I want to find displacement. That's S of 2 and S of 4. Those are the two numbers I need. I need to know what the position is at 2 and 4. I take 2, I plug it in. 4 cut in half is 2. 2 minus 4 is -2. Plug in 4, 16. Cut it in half is 8. 8 minus 4 is 4. If I want to do displacement, I'm going to take my ending position minus my starting position. 4 plus 2, it's 6. And that makes sense. If we threw this on a number line, we are going from -2 over here all the way to 4. And if I went from -2 to 4, I traveled 6. So my displacement is 6. Next thing we want to try to do is find the average velocity, or in other words, the average rate of change over the interval from 2 to 4. To find the average rate of change, that means slope. Y sub 2. Well, that's my y sub 2. 4 minus y sub 1, -2. All over x sub 2 minus x sub 1. That's 6 over 2. It's 3. That is my average rate of change. This 3 right here is going to represent my velocity, my average velocity over that time period. I took the displacement on top. This was my displacement, and I divided by time. That tells me my average velocity. All right. This is the most important thing on this paper, I would say. When we talk about S of t, that is always going to represent position. Okay, I told you a second ago, they could also use x of t when they're mean. If you look at the derivative of position, the slope of position, that's what we did on that last question. We found the slope. The slope of position is velocity. Okay, the slope of position, the derivative of position is going to tell me velocity. Okay, and so that is really important. The derivative of position is velocity. Let's write that down here. V of t represents velocity. Then we're going to do the second derivative of position. So think about what the second derivative of position is. That's like the derivative of velocity. So two derivatives of position, or just the first derivative of velocity. Think about what that means. That's the change in velocity. Think about in your car. You're going 60 miles per hour. That's your velocity. And then you want to change that. What do you hit on your car to change the velocity? You hit the gas pedal, otherwise known as the accelerator. The derivative of velocity, the change in velocity is going to be acceleration. A of t. A of t is acceleration. This creates a little order here that's going to be very important. We always kind of start off with position, where something is. If we take the change in position, the change of position is the velocity. That's the derivative. If we then took the change in velocity, took the derivative of velocity, that's going to tell me acceleration. That's a really important key here. So we could also say this, v of t is velocity. So what if I looked at v prime of t? What if I looked at the derivative of velocity? Oh yeah, that would be acceleration. All right? That's a key concept. I would put a big old star by this thing right here. You need it a lot. We're going to do it all the time. I would say memorize it, but you have no choice but to memorize it because we're going to talk about it so much. All right? Let's look at some graphs on this and understand what's going on here. So instantaneous velocity, that's what we care about. Not average velocity is so much. Average velocity is when we take the slope. That's like, hey, I was going 60 miles per hour during my trip. We want to know the instantaneous velocity. When your time was 7 seconds, how fast were you going at that point? Okay. That, if we're talking about velocity, velocity is the derivative of position. Okay. I want to know the derivative. When the velocity, so, okay, sorry. This is a very important concept. When the velocity is positive, the object is moving forwards, okay? Or sometimes we might say to the right or up. All of those things mean the same. If you're moving forward, you're moving right, you're moving up. Those all represent a positive velocity. If your velocity is negative, that means the object is moving backwards. Okay, if your velocity is negative, your object is moving backwards. You could also say the left or down, depending on the problem. All kind of apply depending on the situation. And then this last concept is really important as well. Speed. When we talk about speed, speed is the absolute value of velocity. Okay, you can be going 60 miles per hour forward. You can also be going 60 miles per hour backwards if you hit the gas pedal hard enough. But in calculus class, instead of saying 60 miles per hour forward or 60 miles per hour backwards, 60 miles per hour would be forward because it's positive. And negative 60 miles per hour means you're going backwards, you're going to the left. If we're talking speed, we're doing the absolute value of that. Or in other words, we don't care positive or negative. We're not looking at that. All right? So speed is the absolute value of velocity. Basically, it's your velocity without the sign. Let's look at it. We've got a graph right here. This is a position graph. One of very few times, notice here that they use the letter X to represent position. One of the very few times that I will give you a position graph. It's not something we do. We often will give you a velocity graph normally when we ask these questions. But this is a position graph. Anytime I give you a graph, I would suggest labeling it pretty big and put an underline on it because that'll always kind of get you in the right direction. All right. When is the particle moving forward? And you can think about this in lots of different ways. But again, we said the particle is moving forward when the velocity is positive. It is moving forward when the velocity is positive. What am I looking for on this graph to decide when the velocity is positive? It's a position graph. How is position related to velocity? Velocity is the derivative. Velocity is the slope. So if I want the velocity to be positive, I want to have positive slope. So when on this graph am I moving forward? Well, from 0 until 2, I am moving forward. And that makes sense. My position is 1, then my position is 2, and 3, and 4, and 5, and 6, and 7, and 8, and 9, and 10. I'm getting further and further away from 0. I'm moving forward. 0 to 2 because I had positive slope, because that means velocity is positive. When is the particle moving backwards? Well, if I'm moving backwards, I want to know when velocity is negative. So when is my velocity negative? My velocity is negative when the slope of position is negative. So I'm moving backwards from 2 until 3.5. Notice that I'm using brackets here. Anytime we talk about velocity, we're going to use brackets. When is the particle standing still? Well, a particle is going to stand still when velocity is 0. So on this graph, I want to know when the slope is 0. The slope is 0 on this graph from 3.5. I'm going to assume that this graph goes on forever and ever and ever just because I can. So 3.5 to infinity. Boom. That's when it's standing still. I'm going to assume that it's not moving anymore because of what's going on. When did the particle change directions? So hopefully you can think about that. When did it change directions? It changed directions at t equals. Notice that it's not an interval anymore. It's not during this time. It's at a single moment in time. It changed direction at t equals 2. Because at t equals 2 right here, velocity changed signs. V of t changed signs. Velocity changed from a positive slope to the position changed from positive slope to negative slope. So if position changed slope, that means velocity changed signs. Velocity went from positive to negative because velocity is the derivative. It's the slope of position. Hopefully that makes sense, and we should get a lot of practice at this by the time we get done, so hopefully it'll make more sense as we go. All right, let's try one more here, and then I'll break it into a second video. I'm tired. I need to go to sleep. Example 5. This time we are given a velocity graph. This is v of t. This is velocity. All right, so velocity graph. When is the particle moving forward? A particle is moving forward when velocity is positive. Well, you got to think about, what is this graph? This is a velocity graph. And so if I want velocity to be positive, I want to know when this graph, this is a graph of velocity, when is it greater than 0? It is greater than 0 right there where I highlighted, okay, because it's above the x-axis. And so velocity is positive from 6 until 12.5 because velocity is positive. Velocity is positive means that the particle is moving forward, and that is when it's above the x-axis. When is the particle moving backwards? Well, a particle is moving backwards when velocity is negative. Well, guess what? This is a graph of velocity. So if I want to know when velocity is negative, I want to know when it's below the x-axis. So you can look right here, and anything that's going to be blue is going to count here. And so that means I'm looking from 2 until 6. And 12.5 to 19. Yuck. But that's fine. Why is that true? Why is it moving backwards? Because velocity is negative. This is a graph of velocity. It's below the x-axis. That means velocity is negative. What is happening from 7 to 12? So let's look at from 7 to 12. So here's 7. Here's 12. What's happening there? This is the most missed question. What is true about this is a graph of velocity. This is a graph of velocity. Velocity is constant. So think about what's happening in your car. If you're in your car and your velocity is constant, you continue to go the same speed. What is happening? I mean, this is kind of a silly answer, but I'm going to say you put it in cruise control. That's not a calculus answer, but it makes sense, I hope, that you're just constantly going 2 miles per hour. You're not going faster or slower during that time period. You're traveling a constant speed, a constant velocity during that time period. This is the calculus answer. This is the real world answer of what happened. When does the particle change directions? A particle changes directions when velocity changes signs. A particle changes directions when velocity changes signs. So when does velocity change signs? Velocity changes signs at 6. Boom, because velocity, this graph went from negative to positive at 12.5 because I went from positive to negative. Velocity changed signs. If your velocity changes signs, that means you are changing directions because a positive velocity means you're going forwards, a negative velocity means you're going backwards. So if it changes, signs going to change directions. What is the maximum speed? Remember, this is a graph of velocity, and if I want to talk about speed, speed is the absolute value of velocity. And so when is the velocity the biggest, or what is the maximum speed? The maximum speed is 6, not negative 6. That's when it's the furthest from the x-axis. Okay, up here we get it to a speed of 2, but down here we get to a speed of 6. It is negative 6, but we do absolute value of it, so it's 6. And then it gets to this last question here that can be confusing at times. When is the particle speeding up? Okay, this could take us a long time to explain it, but think about it. When am I speeding up? A particle is speeding up when you are moving faster. Okay, when you continue to move faster and faster and faster. There are two different things you are looking for. Okay, think about you're in your car. Right here, you're in your car right here, and my velocity is -1, and then my velocity is -2, and then my velocity is -3, and continues -4, -5. Well, what's happening? Your velocity is getting, maybe your velocity is getting smaller, but your speed is getting bigger because it's going -1, -2, -3, or 1, 2, 3. Right here, I am speeding up. That seems weird, but I'm speeding up right there. Okay, from 2 until 5, I'm speeding up because my velocity, my speed is getting bigger and bigger. It's getting further away from the x-axis. And then from 5 to 6, my velocity is getting smaller because my speed is getting smaller because I'm going 3, 2, 1, 0. I'm approaching 0. It's getting smaller. And then from 6 until 7, I'm speeding up again. Because think about it, my speed goes from 0 to 1 to 2, 6 to 7, I'm speeding up. And then there's one more time I'm speeding up. See if you can find it. I'm also speeding up from 12.5 to 14, 12.5 to 14. It's hard to count. 12.5 to 14 right there. From 12.5 to 14, I'm speeding up because I'm getting further and further away from 0. Think about your speedometer. When are you speeding up? When your speedometer gets further and away from 0. And so my speed is going from 1, 2, 3, 4, 5, 6, 7. You are speeding up. When we talk about speeding up and slowing down, and this is kind of a side tangent, but an important one. Speeding up versus slowing down is all about velocity versus acceleration. And you got to think about this a little bit. Velocity versus acceleration. Velocity is easy. They will give this to you normally on a velocity graph. What am I looking for on this velocity graph to tell me the acceleration? If I've got velocity and I want to know about acceleration, if I've got velocity and I want to know about acceleration, I want to look at the derivative of velocity. Or in other words, I want to look at the slope of velocity. That's what I'm doing here. I want to know the slope of this graph. So acceleration is the slope of velocity. And here's how you can tell if you're speeding up or slowing down. Are the sign of velocity and the sign of acceleration the same? Okay, so let's look at it. Right here. My velocity is negative because I'm below the x-axis. This is a graph of velocity. My acceleration is also negative because I have a negative slope right there. Velocity and acceleration, if they have the same sign, we're speeding up. Let's pick another point like right here. At that spot right there, my velocity is negative because it's below the x-axis. This is a graph of velocity below the x-axis. My velocity is negative. My acceleration is positive because I have positive slope. I'm looking at the derivative of velocity to tell me acceleration. At that place, since these two are different signs, I am not speeding up. I'm slowing down. Anywhere you have the same sign speeding up, different sign slowing down. Look at one more right here. Velocity is positive because I'm above the x-axis, and this is a graph of velocity. Acceleration is positive because I have positive slope right there. Velocity is positive, acceleration is positive. That is why we're in the speeding up category. Hope that helps. I will come back tomorrow and I will continue to finish the notes for you. Again, you're finishing the notes and working through the examples. That helps?